Hello, in this video, we are going to use that definition of the sequence of partial sums to determine if a series converges or diverges. So as a reminder from the last video, a series converges if its sequence of partial sums converges. All through the rest of this section, when we're talking about series, we're going to get lots of tests to determine if a series converges or not. But the base definition that we're working with is if there is a sequence of, if we can look at the sequence of partial sums and figure out if that converges or diverges, then we can tell if the series converges or diverges. So our first example here is the sum n equals 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1. And this is a series known as a telescoping series. There is not, when we start getting into tests, a telescoping series test. But when we see two terms being subtracted, it often points towards looking at the partial sums and seeing if by definition, does it converge or diverge. So, looking at the sequence of partial sums. So our sequence itself, just the sequence, is a sub n is equal to e to the 1 over n minus e to the 1 over n plus 1. That is the sequence. The sequence of partial sums is taking this sequence and adding up the first few terms. So the first partial sum is e to the 1 over 1 minus e to the 1 over 2. Just plugging 1 in to n. Not much simplifying can be done there. We just have e minus the square root of e. S sub 2 is adding that s sub 1 plus the next term. So the next term would be plugging 2 into this sequence, which is e to the 1 over 2 minus e to the 1 over 3. If you notice, these e to the 1/2 cancel. S sub 3 is e to the 1 over 1 minus e to the 1 over 2 plus e to the 1 over 2 minus e to the 1 over 3. Plus, now the third term, which is plugging 3 into our sequence. E to the 1 over 3 minus e to the 1 over 4. More things cancel. Now, looking at one more term, s sub 4 would be e to the 1 over 1 minus e to the 1 over 2 plus e to the 1 over 2 minus e to the 1 over 3 plus e to the 1 over 3 minus e to the 1 over 4 plus e to the 1 over 4 minus e to the 1 over 5. Bunch of things cancel again. And hopefully we're seeing the pattern that if we continued this at any level s sub k, what we will get is we'll get that first term, e to the 1 over 1, or e to the first, minus this very last term. But notice the numbers here. The thing that's not going away is the k plus 1 part of our sequence, or the n plus 1 part. So for the kth partial sum, the last thing that doesn't go away is the e to the 1 over, since our variable is k plus 1. That is the definition for our sequence of partial sums. For the series, n equals 1 to infinity, e to the 1 over n minus e to the 1 over n plus 1 to converge the sequence s sub k, which is equal to e to the first minus e to the 1 over k plus 1, must converge. And for a sequence to converge, we look at its limit. So the limit of the sequence of s sub k is the limit as k goes to infinity of e to the first minus e to the 1 over k plus 1. E to the first isn't controlled by k, that stays e. E to the 1 over k plus 1, 1 over k plus 1 goes to 0 as k goes to infinity, and e to the 0 is 1. So the limit of the sequence of partial sums is e minus 1, meaning the sequence of partial sums converges. Therefore, the series n equals 1 to infinity, e to the 1 over n minus e to the 1 over n plus 1 converges by definition of series convergence. To e minus 1. Okay. So right now, to tell if a series converges or diverges, we look at the sequence of partial sums. One more example of this. We want to determine if the following series converges or diverges. Once again, the only tool we have is this partial sums. And this sequence is such that we need to find some way to write it so we can easily look at a partial sums and see if we can find a pattern. Basically, this is a sequence where we can use partial fraction decomposition on 2 over k squared plus 2k, which is equal to 2 times k over k plus 2, which is equal to partial fraction decomposition a over k plus b over k plus 2. And solving this out, we'll get 2 equals a times k plus 2 plus b times k. Gathering coefficients together, this will give us two equations. 2 equals a times 2, and a plus b equals 0. Because we'd have a k plus 2a plus bk. This equation, 2 equals a times 2, means a equals 1, and a plus b equaling 0 means b equals -1. So this series is actually the series k equals 1 to infinity of 1 over k plus -1 or minus 1 over k plus 2. We're going to work with this version. So just like last time, we want to look at the sequence of partial sums. So writing out the first few terms. Again, our sequence is 1 over k minus 1 over k plus 2. So our first partial sums, s sub 1, would equal 1 over 1 minus 1 over 3, plugging 1 into each term. S sub 2 is 1 over 1 minus 1 over 3, plus 1 over 2 minus 1 over 4. Nothing simplifies down yet. S sub 3 is 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5. S sub 4 is 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5 plus 1 over 4 minus 1 over 6. And we're starting to see a bit of a pattern of things canceling. Writing out S sub k, it's 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5 plus 1 over 4 minus 1 over 6 plus, and we continue up, and eventually we'd be plugging in k minus 1 here. And when we plug in k minus 1, we would get 1 over k minus 1 plus 1 over k minus 1 plus 2. K minus 1 plus 2 is k plus 1. Then plus, and when we plug in k, we'd have 1 over k minus 1 over k plus 2. And looking at the pattern from before, we know the 1/3 cancel, we know the 1/4 cancel. And the pattern would be that 1/5 would cancel with something in here. 1/6 would cancel with something in here. But then we'd start canceling the early terms. This 1 over k minus 1 would cancel with something in that dot, dot, dot. If you notice, it's the last terms. The first part of the last terms get canceled. And the first part of the last terms get canceled with something inside that dot, dot, dot. So S sub k, after everything cancels away, is 1 over 1 plus 1 over 2. Everything else goes away until plus, so that should be a minus there, sorry. Minus 1 over k plus 1 minus 1 over k plus 2. And for the series to converge, of 1 over k plus minus 1 over k plus 2 to converge, S sub k, which is equal to 1 over 1 plus 1 over 2 minus 1 over k plus 1 minus 1 over k plus 2, needs to converge. So we look at that limit, k goes to infinity of 1 plus 1/2 minus 1 over k plus 1 minus 1 over k plus 2. 1 stays. The 1/2 stays. 1 over k plus 1, as k goes to infinity, that fraction will go to 0, and 1 over k plus 2 will also go to 0. So the limit of this sequence is 3/2. Therefore, our series k equals 1 to infinity 1 over k minus 1 over k plus 2 converges by definition of series converges, series convergence, because what that 3/2 tells us is that the sequence S sub k converges. The sequence of partial sums converges. So to tell if a series converges or diverges, right now, we are going to look at the sequence of partial sums.